Hello everyone, welcome back to our second video. Today we will be talking about circles and we will go over some theorems that you might want to know and some problems that are pretty common in competitive math. And yeah, we'll see how it goes. So first we're just going to start off simple. Everyone probably knows that the area of a circle can be written as pi times the radius squared, where the radius is the distance from the center out to any point on the circle. So all of these are the same. They're all considered the radius. They're all equidistant, and that is our area formula. However, one interesting thing about circles is that we can calculate the area of a sector, which is what this is called, right in here. And this we can calculate by knowing the central angle. Let's call it alpha. And this angle is going to be helpful in calculating the proportion of this sector to the area of this sector to the area of the entire circle. So we know that an entire circle is 360 degrees if we go all the way around. So what that means is that this sector is going to be alpha over 360. The area is going to be alpha over 360 of the entire circle. So we can multiply this fraction times pi r squared. And that's going to be the area of this sector. So then what we can do is we can use that knowledge in similar fashion to calculate the arc length. And the arc length is what we call this distance right here of a sector. Using the same method, we know that the circumference of a circle can be written as 2 pi times the radius. Let me just write that. And then we also then can calculate this distance, which similarly is going to be alpha over 360 times 2 pi r. So we can see here how helpful it is to know these central angles, because we can calculate ratios and proportions and find areas and arc lengths of sectors. Okay, now we're going to talk about the different angles and how they relate to each other in circles. So let's start off with some definitions. Here, we call these central angles anything that has a vertex at the center of the circle and the two radius are the sides of the angle and they go out to the edge of the circle. Let's call this alpha. The measure of this angle is always equal to the measure of what we call a minor arc right here. So this measure of the arc is alpha. Remember that the measure of an entire circle, 360 degrees. Half a circle then, you can probably guess, 180 degrees. So now let's take a look at what we call an inscribed angle. An inscribed angle is an angle that starts, well, it has a vertex on the edge of the circle now instead of the center of the circle, and goes out to two other points on the circle. These lines that I just drew, we call chords. They basically are lines that connect any 2 points on a circle. So an inscribed circle is two chords which intersect at the vertex which lies on the circle. This angle we can prove always equals 1/2 of its relative central angle right here. So this angle, let's call it A, and let's call this B, where A is a central angle. A equals 2 times B, always. We can now use what we just learned to prove that these two angles, alpha and beta, will always have the same angle as long as they share the same minor arc. This is true for any 2 points that share the same arc. So we take this point, we draw out 2 chords, we make an angle. We take another point anywhere on the circle, and we draw 2 chords to the same point. It will always be the same as that angle. We can use what we just learned to prove this pretty easily. Okay, so first step that we need to do is draw in our center O of the circle and connect it to the 2 points right here that these angles share. Now, from what we just learned, we know that the central angle, which we call this blue angle, is always 2 times the inscribed angle, which we call that right there, if they share the same arc. So if we call this 2x, we know that this must be x. But the same thing applies for this angle right here, because we know that these 2 points are shared by this angle, let's call it A. So that means that if this is 2x right here, then this also must be x. So x must equal x, so we just proved that A equals this angle right here, which we can call B. We're now going to look at something called a tangent. A tangent is a line where if you take any point and you draw it so that it touches the circle, this line segment touches only 1 time the circle, that point right there. Most other segments, if we draw through to a circle, will touch 2. For any given point outside of a circle, we always have 2 tangents. Let's call this point A and this point B. This is C, CA, and CB are tangents to our circle O. Now we're going to look at probably the most important formula that or theorem that you'll come across when solving circle problems in competitive math. It says that if we have a tangent CA to a circle O, the angle CAO, where AO is the radius of the circle, will always be a right angle. We can prove this first by assuring ourselves that distance OA is the shortest distance to any point on line L, and we can call line L our tangent line. We can prove this pretty simply. If we just look at, let's choose an arbitrary point right here and draw it to O, we can assure ourselves that it is longer, because already here we see that we've traversed, or we've gone the distance R, but we still have this little bit more. So this distance OB has to be longer than OA. We can do that same thing for every point along L, but we'll see quickly that OA, which is where A is the tangent point of the of line L to circle O, this line or segment OA will always be the shortest. Now we're going to look at why that is important in proving that CAO is a right angle. Now we want to prove that if we have any point A and a line L, the shortest distance from A to L will always be a segment that is perpendicular to line L. And we can prove this using a contradiction proof, which you'll find are very common as you begin doing more mathematics proofs. Basically, what they say is, assume X, where x is essentially the opposite of what we're trying to prove. So in our case, we're going to assume that this distance that AB is not perpendicular to line L. We're going to assume this. And so our hope now is that we can contradict something that we claim to be true in our assumption. And what we assumed was that AB, the shortest distance to line L, is perpendicular to L. But if we can contradict ourselves by proving that AB really isn't the shortest distance, then we nullify our assumption. We say our assumption is no longer true. And if our assumption isn't true, that means that AB is perpendicular to L, and in turn, the shortest distance from a point to a line will always be a segment which is perpendicular to that line. So now we're going to prove that the shortest distance, so now we're going to hope to show that if AB really is the shortest distance, it has to be perpendicular, or it isn't the shortest distance. So we're assuming that it's not perpendicular, so that this angle right here isn't perpendicular. But what we can show is that if we draw a perpendicular from A to the line, then we form a triangle where AB is the hypotenuse. But what we know about triangles is that hypotenuses are the longest sides of a triangle, which means that AB has to be greater than AC, which is a leg of the triangle. So we just contradicted ourselves because we had claimed that AB was the shortest side. But we just showed that actually AC is the shortest distance to the line. Therefore, our assumption is no longer valid, meaning AB isn't perpendicular, and in turn, by contradiction, we can prove that the shortest distance to a line is always a segment which is perpendicular. Now what we're going to look at is another application of tangents to circles. And this is another really, really important theorem that you need to know for competitive math problems involving circles. What it says is if we take a point outside the circle and we draw its two tangents, remember there's always and only two tangents from a point to a circle. So our one tangent is PA and our other is PB. What we're going to prove is that PA equals PB, always, no matter what point outside the circle. And we can prove this by using what we just proved by contradiction, that the tangent is perpendicular to the radius of the circle. So we have that these angles are perpendicular, 90 degrees, and we can use this to prove that PA equals PB. So if we draw our distance from P to O, where O is the center, we see that we have two triangles that are actually congruent. Because what we have is OB right here, which equals OA because they're both radiuses. Then we know that because this line PO is the same for both, that this side length PO is the same for both triangles. Then we can prove that the two triangles are congruent by side angle side, which some of you may have learned in geometry. It basically says if we have two sides which are congruent and we know they share one angle which is the same, that they're congruent. And we know that they share one angle that is the same because we've proved that they both have this 90-degree angle. Therefore, we know that PAO is congruent to triangle PBO. And if it's congruent, we know that their side lengths are the same for each respective angle. So PA equals PB. And done. That is known as the equal tangents theorem. Now that we've talked about some theorems, some angles, and the different things involved with circles, we're actually going to take a look at some problems But one thing you'll notice that a lot of circle problems in competitive math don't actually use that many complex theorems or formulas. Really, all you have to do is sort of figure out how you can use the information given, whether it's side lengths or radiuses, and sort of convert that using just simple geometry ideas. So we'll take a look at this problem right here. I can read it out loud. In the figure to the right, which I blew up, circle B, which is this circle right here, and then circle C, which is right there, are tangent to each other. They're also tangent to circle A, which is the big circle right there. And what we have is AY and AX are the radiuses. They give us the distance AB, which I labeled for us, and AC they give us 5, and BC. So we know everything there is to know about triangle ABC. They ask us what is AX, which is the radius, so they could also ask us what is AY. It's the same thing. They're really the radiuses of the circle. Now, what we do first is we look at the relationship between AC and AY and the relationship between AB and AX. And the first thing that I notice is that this distance CY is the radius of circle C. So I'm just going to call that lowercase c for the radius of C. And I'm going to call over here the same idea. The distance from B to X is the radius of circle B. Then what I notice is that AY and AX are the same. So I can write out an equation that looks like this. 5 plus C equals 6 plus B. Pretty simple. We know radiuses are always the same. Any point on the circle, it will always be the same. So then we take a look at this CB. They give us 9, and you're looking at it, and you can see actually that the radiuses of C and B are actually what make up this distance CB. As you can see here, this distance is C, and this distance is B. And if we add them together, we get 9. So now we've transformed this somewhat complex, and we have a lot of unknown problems, into a simple system of equations which we can now solve. Because we have 2 variables, 2 equations, we know we can solve it. First thing I like to do is just solve for one variable in terms of the other. So I'm going to say B equals 9 minus C. I just subtracted this C and put it over there. Then I'm going to substitute the B here into the B in my first equation. What it looks like is 5 plus C equals 6 plus 9 minus C. I'm going to simplify, and I get 5 plus C equals 15 minus C. So therefore, 2C equals 10. Easy enough, C equals 5, but they ask us for AY, not the radius of C, but that's pretty simple, or AX, but AX equals AY. So AY just equals C plus 5, which equals 10, but AY equals AX, so we are done, and the answer is 10. Now we're going to take it and look at another problem, which you'll see are pretty common on math competitions like the AMC, where they ask you to solve for a shaded region, which is essentially just one shape sort of subtracted of other shapes or multiple other shapes. So this is a good example of what you might see for a circle problem on math competitions. And the main idea of all of these problems is being able to figure out areas of different shapes using often only like the side length of the biggest shape. So here you can see we're given the side length of a square and of a circle, and from that we're asked to find this weird looking shaded gray area. which might seem a little overwhelming, but we can use the side lengths, and here, right here, we're given a diameter to find the radius and side length of the inscribed shapes, which is a very common thing that you'll need to be able to do for math competitions. So if we first just quickly read the question, it just asks us to find the largest shaded area. So we're essentially just going to have to find the areas of all the gray areas and then just compare them. So we'll start with right here, figure A. We're given the side length of a square, which is 2 centimeters, and an inscribed circle, meaning the circle is inside the square. And if we look closely, we can see that the diameter of the inscribed circle is actually the same but parallel line of this square. Meaning that, and we can show this quickly by just showing that the angles are right. And we know that the angles are right here because this is a tangent line. And what do we know about tangent lines? Right here, if we just call this C and D, we know CD is tangent to this circle A. We know this is a right angle. We proved it. So, and then because these angles are right, we know that these two lines are parallel. And because they're parallel, we know that this radius of A has to be 1/2 of the side length. And we can see that a little bit easier if we just see the diameter as a whole is 2, and then the radius is 1/2 of the diameter. So the radius is just 1, this right there, and then we have another one there, because the two radiuses will make up the diameter. Then we know that our formula for this circle is pi r squared, the area. So area equals pi times 1 squared, which just equals pi. But then they ask for the shaded area, not the circle. But we know that the circle is taking up part of the square, and if we subtract that from the area of the square, we're just left with the gray areas. So the area of a square is the side length squared, so 2 times 2 minus pi, which is square area right there and circle area right there. We're left with 4 minus pi. Now moving on to figure B, it's similar, except here we have 4 inscribed circles that are all tangent to each other. It looks even more confusing, except actually what we have is, instead of the diameter of the circle being the side length, we have the diameter of the circles being 1/2 the side length. So it's the same idea, just a little bit different. And so we can see that if you actually take 2 diameters of the circles, because they're connected, so like look up there, it's really just the same as this side length. It's the same idea as we used in A. We can prove it. These lines are parallel, which means that their distance have to be the same, which means that the 2 times the diameter of one of those small circle has to equal the square side length, which is 2. So the diameter of one of those circles is 1, which means the radius is 1/2 of that, 1/2. So the area of one of those small circles is pi times 1/2 squared, which equals pi times 1/4. However, we have 4 of those, so we need to multiply it by 4 for the area of all of those circles. So the area of the 4 equals pi. Then we notice that if we subtract those circles, we are left with the gray area. So we do the same thing, we get 4 minus pi, but we notice that that's the same as A. So we'll just keep that in mind because they ask which shaded area is the largest. So A and B are the same because the area of one of these circles is 1/4 of the area of this big circle. Now we're going to take a look at C and see what the area of its shaded region is. So the first thing we notice is now we have an inscribed square, meaning the square is inside the circle. So how is the diameter, which they give us, 2 centimeters of C related to this square? Well, what we notice is that an inscribed square's diagonal is actually the diameter of a circle. And this is provable by looking at what we learned earlier with central angles and inscribed angles. Remember that the inscribed angle is the angle from a point here, let's look at this one, on the circle out to any other points on the circle. So this is an inscribed angle, and we know because it's a square, it's 90 degrees. But what we remember is that the central angle, which is if you go from the center of a circle out to 2 points on the circle, and if they're the same as the inscribed, it has to be 2 times the inscribed angle, which means that if this is 90, this has to be 180. But this central angle is only 180 if it passes through the center and is the diameter. So therefore, we've proven that the diameter of the circle is really the diagonal of a square. Now we can look at this diameter right here as 2 centimeters because we know that it's given in the problem as 2 centimeters. But we also know that that means the diagonal of a square is 2 centimeters. And the diagonal of a square and its side lengths form a 45, 45, 90 triangle, meaning these angles are 45 and this is 90. And we can see that because right here we have a 90-degree angle, and then it has to be an isosceles triangle because the side lengths of a square are equal, so that this x and x are the same. If we do Pythagorean theorem, which we learned earlier, we know that the hypotenuse, which in our case is the diagonal of a square, so x squared plus x squared equals the diagonal, or the hypotenuse, squared. Therefore, d, if we simplify, equals x times the square root of 2. Thus, if the diameter, or diagonal, equals x times the square root of 2, and the diameter is 2, the diagonal is also, we have 2 equals x times the square root of 2. Remember, x is our side length of the square, so x equals 2 over the square root of 2. But we want the area of the square because we want to subtract it from the circle area to find the gray areas. So the area of the square equals x squared, which equals 4 over 2, which just equals 2. Now we want to calculate the area of the circle, so we can subtract away the area of the square. And that equals pi times radius squared. Remember, the radius is half the diameter is 2, so it's pi times 1 squared, which just equals pi. So now we have that the area of the square equals 2, and the area of the circle equals pi, so the graded area, the shaded area, equals pi minus 2 because we just subtract the circle and the square to get what's left, which is the gray. So now we have to compare all these because the question asks which is the largest area. Well, if we look closely, we can do a little bit of estimation because at first it seems a little weird. We have to subtract pi's. It's a little weird. Here we have 4 minus pi, both for a and b, and here we have pi minus 2. But remember, pi roughly equals 3.14. So if we do a little bit of subtraction, just rough estimation, we get 4 minus 3.14 equals 0.86. Here we have 3.14 minus 2 equals 1.14. So we see that 1.14 is bigger, so C has the largest shaded region. And that's all for this video. We will be publishing a problem set of related circle problems and combining what you learned using triangles earlier. And if you have any questions, always email us, or you can at the end of the week, log on to a Zoom where we'll be answering questions. Thank you.